Hello all. In continuation to the previous mechatronic design of mobile robot, welcome to our session on sensor selection, actuator selection, control system design, and the following prototyping and deployment steps. Welcome to our second video. So, following uh, the design on concept screening and concept scoring. So we are going into the sensor selection. So as far as our problem statement is concerned, we should be able to follow a definite path. Static obstacles should be detected. Dynamic obstacles should be detected, which is an intruder, and then the encoders to measure the distance traveled by the robot should be also be calculated. So we are selecting the following sensor, which is a Kinet Xbox 360 sensor, which is already available in the market. The main constraint of this sensor is it can be able to work in a range of 0.5 meters to 2 meters, okay, which is more than enough for an indoor environment. So the Kinet Xbox 360 is used to follow a definite path. So the main objective or the main methodology of doing the surveillance operation with Qbot system is to draw a definite path along the sides of the lab, and the robot will be moving following the path. Okay, so an obstacle detection, static obstacle detection will be done by the robot by using Kinet Xbox 360. So it will be able to do collision avoidance, obstacle detection, and collision avoidance. Okay. So dynamic, obviously, intruders should be detected. So all the dynamic obstacles are considered to be intruders, and then it reports to the uh, main control station, and the distance traveled by the robot is uh, calculated by using encoders. Okay, these are the sensor selection. So actuator selection is the movement of the robot. The movement of the robot is controlled by motors. Okay, controlled by motors. So obviously, as I said in the previous step, the robot consists of two drive wheels. So the maximum torque which is applied on the robot is calculated from the payload of the robot, and um, after calculating the maximum torque, the motor is being selected. Okay, so the weight of the robot is approximately 3 kg. External load maximum to the maximum 2 kgs will be applied. So the total weight of the robot is considered to be 5 kgs. So maximum speed is 50 rpm. Thickness of the shaft, motor shaft is, or radius of the motor shaft is 0.004 meters. So we're calculating the maximum torque. So the first step is to calculate the force. So F is equal to m into a. So 5 kg into 9.81. So you're getting 49.05 newtons. So the total torque required to drive the robot is torque is equal to force into distance. So you're calculating to be force 49.05 into distance, diameter, radius of the shaft, which is 0.004 meter. So you're getting 0.198 newton meter. So since there are two motors which we have considered, the total torque given by the two motors as a whole should be greater than 0.198 newton meters. Okay. So here calculating the current in this slide. So for that we are using the maximum speed. So maximum speed 50 revolutions per minute into 0.105 radians per second. equal to 5.25 radians per second. We have converted revolutions per minute into radians per second. Okay. So in the next step, the power is calculated. So P is equal to T into omega 0.9198 Newton meter, as we have calculated above, into 5.25 radians per second. We are getting 1.03 watts. So if the supply voltage is 12 volt, so I is equal to P by V. Supply voltage, if you consider as 12 volt, so we have calculated 1.03 watts divided by 12 volts, which is 0.08 amps. So the maximum current for to drive the robot is 0.08 amps if we consider 12 volts battery and 5 kgs payload at an rpm of 50 uh, radians per second. Okay. Okay. So this is how we calculate the current drawn by the motor. So as far as the payload of the motor of the robot increases, these calculations will vary. Okay. So this is detailed mathematical modeling. The next step. So a mathematical model is a description of a system using mathematical concepts and language. The process of developing a mathematical model is termed as mathematical modeling. Okay. So simple mathematical technique, as far as we know, we are using quadratic equations and transfer functions. So input parameters and output parameters. So these are the basic input parameters and output parameters which we consider. So the left wheel velocity, right wheel velocity, and the distance between the wheels of the robot. Then the forward output parameters are forward linear velocity, angular velocity omega c, and the coordinates of the target to the control station x comma y. These are the equations. Vc is equal to half Vr plus Vl. Omega c is equal to theta dot, or equal to 1 by d into Vr minus Vl. So these are the xy coordinates which we measure according to the variable theta, the angle of rotation of the whole robot, or otherwise we can calculate the coordinates directly from the encoders. Okay. So this is control system design. So this is the basic model of a control system, which is a computer bar microcontroller, which is the center of the control system, and it controls the plant via actuators. The actuators are powered by using power amplifier, which receives power from a DAC. Okay. Then the plant is giving output to the sensors. Output. Sorry, the plant is giving outputs. Uh, okay, those outputs are sensed by the sensors, and those outputs are seen via a scope. So via a scope we are seeing it. Okay, then a function generator. Function generator may be an AC, DC, or anything. So these are basically DC set points. So a control algorithm and a model. These are the basic two things which is needed for a control system design. Okay. Okay. So the next thing is controller. So we are using an embedded Linux developed 2016 computer in this system. The controller platform is Linux. The algorithm is developed basically in MATLAB software and is downloaded via Wi-Fi communication to the controller. Okay. The controller, after embedding the program into the system, so we are using C code. We are converting that code into C code, and we are using it into the system. Okay. So PID controller is not used in this robot, and hence jerk is there in the robot. So this is the first control algorithm. So the first thing is to start and to drive the motor and along direction along the same velocity, and is moved along a marked line in the center for robotics lab in a definite path. So second step is detect the presence of any static obstacles along the path and avoid the obstacle. So while moving, if there is any static obstacle, it should detect via the Xbox 360 sensor, and it should be able to drive the motors in if it has to move in the right direction, the microcontroller should drive the right motor in a velocity less than the left motor. So it should be able to avoid the path. Okay. So next, the detection of the dynamic obstacles. Dynamic obstacles. Again, the intruder. Okay. Then, if the intruder is a phone, then the robot turns and moves near to the intruder. While every movement of the robot, the the activities or coordinates of the robot is being monitored by the control room. Okay. Then the coordinates are when it reaches near to the intruder, coordinates are shared to the operator about the intruder information. Then this is image processing algorithm. How the kinet sensor works and how it moves. Okay. So basically, RGB image is obtained from the kinet sensor. Uh, so that is the first step. Image is processed. The threshold value of the image is calculated. So all the blobs of the object are determined, and the centroid of the detected largest blob is determined. So if the target is in white color, uh, so the largest white blob will be calculated and it will be targeted, and the object should be moving. Okay. So by using the centered value, we drive the robot to the intruder. By calculating the largest blob, and when it moves, when the xy coordinates uh, moves, we are following the particular intruder. Okay. Then hardware in loop simulation. Hardware in loop simulation is a type of real time simulation. Like it is used to test your controller. Okay. Then HL simulation shows how your controller responds in a real time to realistic virtual stimuli, and to determine if your physical system plant is valid. So we are putting the equations in this in a model which is programmed in MATLAB, and we are using this model to control the robot. So basically, in forward kinematics, so in this step, forward kinematics. The kinematics of the robot will be VR, and VL will be given as input, and VC and omega will be calculated. X dot, Y dot, and theta dot. X, Y, and theta of the X dot, Y dot, and theta dot will be calculated. Okay. Now depending on the X dot, you can integrate and calculate the X, Y coordinates. Okay. So otherwise you can use this encoder system, and you can find the coordinates of the robot. So this is deployment of embedded software. Okay. So as I said, embedded software is uh, is a piece of software that is embedded in hardware or non-PC devices. Okay. So it is written specifically for the particular hardware that is runs on, usually has processing and memory constraints because of the device limited computing capabilities. So in this system, Quark software is used with the MATLAB 2016 B for Quanza series, and is deployed into the programming PC. So these are the references which I have taken. So conserve manual. So some links, YouTube links, and Mechatronics by Bolton, and Mechatronic system designed by Devadas Shetty. So thank you for watching. Thank you.